Imagine harnessing the power of the sun, only to have it threatened by the invisible force of the wind. What if we told you that scientists have cracked the code to make solar panels more resilient? In the Western Cape of South Africa, researchers embarked on a 109-day journey to understand wind's impact on PV panel mounting rails. They meticulously measured wind loads on two instrumented PV module mounting rails, comparing real-world data to the AS7-22 design standards. Full-scale experiments like these set the benchmark for future research, says Johannes Hendrik Kokiemoer, highlighting the importance of their work. The study focused on Omega-type cold-formed steel mounting rails, crucial for the structural integrity of large PV installations in windy, flat terrains. The site, a dedicated PV research field, featured 6 rows of PV panels, with the critical measurements taken from one specific row. Interestingly, the maximum wind loads were recorded for easterly winds, revealing the vulnerability of PV panels to certain wind directions. The data showed that while torsional responses were similar, Rail B experienced higher bending mode responses due to its position on the torque tube. Comparing their findings to AS7-22, the researchers discovered lower combined wind load coefficients, a promising insight for future PV designs. This groundbreaking research, published in the Journal of Wind Engineering and Industrial Aerodynamics, paves the way for more resilient solar energy systems. Stay tuned for more innovations in renewable energy. Scientists in South Africa have conducted full-scale research on the effect of wind load on PV panel mounting rails for more than 100 days. Compared to standard design codes, they found lower combined wind load coefficients. Maximum loads occurred for an easterly wind direction. A group of researchers from South Africa has conducted a full-scale field measurement of the wind load effects on the mounting rail of a PV single-axis tracker. The data was collected over 109 days in the South African province of Western Cape over 2 instrumented PV module mounting rails. Actual results were also compared to AS7-22 estimations, the American Society of Civil Engineers standard for design loads. Full-scale experiments such as these are important to provide a reference or targets for future research using wind tunnel modeling or simulation, corresponding author, Johannes Hendrik Kokiemoer, told PV Magazine. The current investigation considers wind load effects in an Omega-type cold-formed steel mounting rail. The rail is connected to the torque tube at mid-span and bolted to the PV modules at each end using a total of 4 anchor bolts, said the academics. The inherent large surfaces and lightweight support structures mean that wind loading considerations govern the structural design of large PV installations. This is exacerbated by the fact that PV installations are typically located in flat exposed locations associated with higher wind loads. The measurement occurred between December 2022 and March 2023 in a site dedicated to a variety of PV-related experiments that has a wind exposure category C per the AS7-22. This field consisted of 6 PV rows, approximately 32 meters long and spaced 5 meters apart, using a 101 mm by 3 mm circular hollow section torque tube connected to a central swing-arm drive system. Torque tubes were mounted on polymer bearings connected to 76 mm by 4 mm circular hollow section piles. While 5 of the rows participated in different research, the measurements mentioned were taken in one row. It consisted of 2 instrumented rails with 2 PV arrays installed in various positions. The PV on rail A had a length of 2.108 meters, width of 1.048 meters, and a mass of 24.3 kilograms and was positioned at the exposed outer edge of the array, while rail B had a length of 2.037 meters, width of 1.005 meters and a mass of 25 kilograms, and was located inwards from the edge of the array. Both had tilt angles of -55 to +55. The frequency content of measured loads showed contribution of the fundamental torsional mode at 3.5 Hz, zeta 1 equals 0.5%, and the secondary bending mode at 4.7 Hz, zeta 2 equals 0.2%, to the measured response of rails A and B, the research group stated. While the torsional response was similar between both rails, rail B showed a significantly higher bending mode response compared to rail A. This was likely due to the position of rail B on the torque tube, where the bending mode can more easily be excited. The scientists also found maximum loads occurred for an easterly wind direction when the measured row was more exposed compared to a westerly wind direction. The measurements also showed that the dominant wind direction was south and that this direction is favorable as it is not perpendicular to the rotation axis. However, high wind speed events may still occur in more critical non-dominant wind directions, as seen for the maximum measured wind speed in this study, they added. The experimental results were compared to coefficients for fixed tilt systems from AS7-22. For normal forces, the peak static coefficients for rails A and B ranged between 2.0 and 2.1, which is lower than the code values ranging between 2.4 and 4.6. The corresponding dynamic coefficient ranged between 0.7 and 1.0, which is within the code's range of 0.4 to 1.5, the researchers explained. The experimental static moment coefficients ranged between 0.36 and 0.40, and compare favorably to code values ranging between 0.29 and 0.64. The dynamic part indicated values of between 0.22 and 0.23 for the experiment, compared to code values ranging from 0.29 to 0.64. Their findings were presented in Field Measurements of Wind Load Effects in a Photovoltaic Single-Axis Tracker Mounting Rail, published in the Journal of Wind Engineering and Industrial Aerodynamics. Academics from Stellenbosch University and the South African chapter of renewable energy systems company SCATEC conducted the research.